So what is the orthogonal diagonalization of a matrix, and when and how can we do it? Well, the orthogonal diagonalization of a matrix A is the representation of A as the product of three matrices, Q, D times Q transpose, where Q is an orthogonal matrix, which just means that its inverse is equal to its transpose, and D is a diagonal matrix. So the question is, which matrices can we write like this? And it turns out that they're exactly the symmetric matrices. So the main thing that I want to explain in this video is how to take a given symmetric matrix, A, and produce its orthogonal diagonalization. So let's first see why orthogonally diagonalizable matrices are going to necessarily be symmetric. So let's take a quick look at just how that would work. So let's imagine we're given an orthogonally diagonalizable matrix. That just means that A can be written as Q times D times Q transpose. Now, if we can write A in this way, then we can ask the question, what is A transpose? And that will just be Q D Q transpose transpose. And this here is just going to be equal to, so how do we calculate the transpose of a product? Well, we reverse the product, firstly, and then we transpose each component. And so we're left with this. Now, this term here, Q transpose transpose, what does it reduce to? Well, just Q. And D transpose, if D is diagonal, then the transpose is just equal to D. And then the last thing is we can do nothing, so we're just left with QT there. So since A is equal to Q D Q transpose, we get that this at the end here is just equal to A. And so what we've shown is that the transpose of the matrix A is just equal to A. So in other words, A is symmetric. Now it will turn out that if A is symmetric, we can also orthogonally diagonalize it, and that's a much more complicated proof, so we won't do it here. And instead, what we're going to do is just move on straight to the procedure for orthogonally diagonalizing a matrix, which will come up in a moment. Here it is. So here is how we orthogonally diagonalize a symmetric matrix. Firstly, this is just a modification of regular diagonalization. So step one is always to first find all possible eigenvalues, lambda, of the matrix A. Then, after that, what we'd usually do is find the eigenspace. So in other words, find all possible eigenvectors for that specific eigenvalue. So we'd walk through each eigenvalue one at a time and then calculate the corresponding eigenspace and then find a basis for that eigenspace. And here's a slight difference. What we're going to actually do is find an orthonormal basis for each eigenvalue. So that is a set of eigenvectors for lambda, which are all orthogonal to each other and of length 1. Okay, so now once we have calculated that set, we can create the matrix Q. And here's how we do that. We create the matrix whose columns are simply the vectors that appear in this orthonormal basis B lambda. So there'll be n of them, and they'll all be different. So we stack them all into matrix as the columns. And then we can create D once we've done that. And the way that we create D is that it's a diagonal matrix, so we only need to say what happens at the entries along the main diagonal. So the entry at j comma j is just going to be equal to lambda if the jth column is an element of that orthonormal set, B lambda. So once we've done this, then the orthogonal diagonalization of A is just going to be given in this way. Okay, so it's a little bit of a wordy process here, but let's just illustrate how this works on two examples. So here's the first example. Just a simple 2x2 matrix here. So let's orthogonally diagonalize this matrix. The first thing to do is step one, which is to calculate all the eigenvalues. So we're looking at the characteristic equation here, which is this. So we're solving here for lambda, which makes this equation 0. And so we're solving this equation, 1 minus lambda minus 2 times 2, which is 4. And this must be 0. So this gives us two possibilities. So I'll just write this a bit differently. So 1 minus lambda squared must equal 4, and it's pretty clear what lambda will be. Lambda must either be equal to -1, or lambda should be equal to 3. All right, so we have just found two eigenvalues, lambda equal to -1 and lambda equal to 3. And so what do we need to do in step 2? Well, in step 2, we need to calculate the eigenspaces for each of these eigenvalues. So let's start at lambda equal to -1. And what is the eigenspace corresponding to lambda equal to -1? Well, it's written like this. So E sub lambda. And what is this? Well, it's the set of all two-dimensional vectors satisfying this equation, right? And what is that in our specific case? We want to calculate what that is. Well, we can do a quick shortcut method. To calculate what this linear system is saying, you can do it directly. You can solve for particular x and y. So you can set x here equal to a unknown 2 vector xy, and then solve for xy, making this true. And we're going to do exactly that with an augmented matrix here. And so how we do that is we create an augmented matrix, zeros on the right-hand side, and then we take this matrix over here and put it in the left-hand side of this. But with just one difference, is that we substitute the lambda equal to -1 for where we find lambda. So to do that, let's see what we get. We will just get here lambda, so 1 minus lambda is just going to be 2, because 1 minus -1 is 2. Then we have 2 here, and then we have 2 here, and also have 2 here. So this is a linear system, and just to be clear what the x and the y is, this column here corresponds to x, and this corresponds to y. And this is a very simple linear system. It reduces in this way. And so immediately we can see what x and y are going to be. So x, which is equal to xy, is just exactly equal to, we have a free variable, y can be a free variable t, and then x plus y should be 0. So in other words, x is equal to -t. So we get -t, t, and so this is just equal to -1 times t. Okay, great. So we've just found what kinds of x's are in the eigenspace here. Okay, good. So next, let's look at lambda equal to, well, in fact, let's not yet look at lambda equal to 3, because what we need to do is find an orthonormal basis for this eigenspace here. Okay, so what will an orthonormal basis be? Well, we can take here, so b -1. It must be a set containing how many vectors? One vector, because this is a one-dimensional subspace of R2. And so which vector? Well, just normalize this vector over here. So divide this vector by its magnitude, and that's what we can take our b sub -1 to be. So just to be clear, this is b lambda. In the case lambda equal to -1. And so here we have -1 over square root 2, 1 over square root 2, and that's our first vector, just because the length of this is root 2. Okay, so let's move on and talk about the eigenspace corresponding to lambda equal to 3. So if lambda is equal to 3, then we're going to do something similar. Again, what are we wanting to solve for? We want to find a description of all the eigenvectors corresponding to lambda equal to 3. So let's just immediately look at the augmented matrix. Again, the first column here will correspond to x, the second to y, and we're thinking about this x being our vector xy. Great, so what is the left-hand part here? Well, now we just go to our matrix here, as we did earlier, and we just substitute in lambda equal to 3. And when we do that, here we'll just get -2, 2, 2, and then -2. And we can solve this further and just get, it's very simple. So this second row here is negative the first row. So again, we're just going to get -1, 1, 0, 0. And here we have 0, 0. And so our x equal to xy is just, well, firstly, y is a free variable, so we can say y is equal to t, and then -x plus t is equal to 0. So in other words, x is equal to t, and to cut the long story short, we just have that x is equal to y. Great, so this vector can be represented in this way, and so we can write our eigenspace as all vectors 1, 1 times t, where t is just a real number. Okay, great. So immediately from this eigenspace, it's one-dimensional subspace, so we just need to find one vector here of length 1, and that's going to be quite simple. We can set b lambda b3, because lambda is equal to -3, is just equal to, let's say, this vector, because t equal to 1 tells us that that vector is in our space, divided by its magnitude. So we have here 1 over square root 2, 1 over square root 2, and that's our vector. Okay, great. So we've found an orthonormal basis for each eigenspace. That's what we've done here. And that's also what we've done here. And so now we're ready to compute the orthogonal diagonalization. So according to our algorithm from earlier, we can say what the matrix Q is going to be. Q is going to be the matrix of columns. So we put here C1 and C2, where C1 and C2 appear from one of these two sets, this one or this one. And here, let's just choose the first column we calculated, so this vector over here, and so we have -1 over square root 2, and here we have 1 over square root 2. And in this column, let's put 1 over root 2, and here 1 over root 2. Great. So that's what Q is. And so in other words, this here is C1, and this here is C2. And that tells us what D is going to be. So D is going to be a diagonal matrix. So it'll be a 0 here and a 0 here. And how do we determine what goes in that position? Well, we check where does the first column go, which set does the first column belong to? C1. Well, C1 belongs here. Here it is, right? So it belongs to B -1. The lambda here is -1. And so for that reason, we put in -1. Great. Now what about C2? Well, similarly, C2, it's not here, but it is here. So it is B3. It's in B3. And for that reason, we put 3 here, the eigenvalue corresponding to this eigenvector. And then you can check. With this particular Q and D, we have a property, and that is that our original matrix A, so A here, if you remember, was just equal to 1, 2, 2, 1, and this will be equal to the matrix Q times D times Q transpose. And I leave it to you to check that. And moreover, what we're going to have is that this Q here is orthogonal, and of course D is diagonal, and then Q transpose is going to be the inverse of the matrix Q. And how would you know it's the inverse? Well, because it's an orthogonal matrix. All right, so that was just the introductory example. Let's take a look at a slightly more complex example. So a 3 by 3 matrix, which is given here. So the question is to orthogonally diagonalize this matrix. Now, this particular matrix actually appears in a different video where we calculated the eigenvalues, which are given here, and we calculated eigenvectors, well, all eigenvectors, which were given here and here. And what are these things here? Well, this turns out to be a basis. So this is a basis for E sub lambda 1. And this one here is, of course, also just a basis for E sub lambda 2. So if you want to see exactly the details of how we get that, you can just check out my video on this exact matrix, where we look at how to calculate the eigenvalues and eigenvectors for that matrix. Okay, otherwise you can just believe me. So this is a basis for the eigenspace. Now what does it mean? It means that if this is a basis, all right, it means that every eigenvector, so every eigenvector for lambda 1 is of the form this one times some number plus this one times another number. That's what it means to be a basis, just with one extra property, namely that these two vectors are linearly independent, and you can very easily check that that's the case. And this is also this one vector here, this set containing one vector, is the basis for all eigenvectors corresponding to lambda 2. Okay, so now we have a problem. These are not orthogonal bases, so that's a bit of a problem because we can't use our theory of orthogonal diagonalization just yet. We have basis for the eigenspaces, but what we don't have is that these vectors are orthonormal. Firstly, we can turn this one into an orthonormal basis pretty easily. How do we do that? We just have to normalize this vector, because there's only one vector, and the only thing preventing this from being an orthonormal basis is that its length isn't 1. So we can turn this into an orthonormal basis, and we can call that B sub lambda 2, or just, if you want, B2. And this is just equal to the normalization of this one vector, and it's 1 over root 3, 1 over root 3, and 1 over root 3. Magnitude of this vector is root 3. Good. So we have found the one orthonormal basis for the eigenspace here. So we just need to do the same thing here. But we have a problem. We can't just normalize this vector and this one, because yes, they would be normal, but they're not orthogonal. Why? Because if I take the dot product here, I take negative 1 times 1, and I add that to 1 times 0, and I add that to 0 times negative 1, I'm going to get, let's label these vectors. Let's call this one x, and let's call this one y. Then if I take x dot y, this is just going to be negative 1. And so, yeah, x is not orthogonal to y. So we need to do something a little bit more tricky here. So I'm going to just look at this problem a bit more generally. So from two vectors, x and y, how can we orthonormalize them? In other words, how can we produce two vectors from them, which are linear combinations of both, but which are orthogonal to each other? So let's take a look at that question. So the first thing is, we're given this vector x. So let's call this one here x. And we're given a vector y. But they're not orthogonal. This angle here is not 90 degrees. But we can make an orthogonal vector which to y from both of these with just a linear combination. So how do we do that? Well, let's consider the vector which goes from x and drops down onto y. Okay? So we want to see what is this vector. This vector here, if we can produce it as a linear combination of x and y, then it will be an eigenvector corresponding to the same eigenvalue as x and y. But how do we produce it? Well, this vector that points from the origin to this point here is just going to be, let's say, some scalar multiple of y. And if we have that scalar, k times y, then the vector which points from here to there is just x minus k times y. Okay, and then we have a very important observation, is that we want this to be orthogonal, which would mean that if we can do this, then we can calculate the value of k. So in other words, if x minus k y is orthogonal to y, then this should be 0. But now dot product behaves like multiplication, so we can distribute the dot in, and we get this. And this will help us calculate what is k, because we can take the k y dot y over and then solve for k. And I'm sure you can see we'll just get k is equal to x dot y divided by y dot y. And another way to write this is just x dot y divided by the magnitude of y squared. All right, so this vector, if we call it w, can be written simply as w is equal to x minus x dot y divided by absolute, well, not absolute value, just the magnitude of y squared times y. And it will have the property that it is, firstly, it's a linear combination of x and y, and it is orthogonal to y. Okay, so that's going to help us in our eigenvalue question. So let's go back there. Sorry, our orthogonal diagonalization question. Because if you remember, what we need to do is from these vectors here, so from this vector here, which we call x, and from this vector y, these are all the eigenvectors which correspond to lambda equal to -1. In other words, it's the eigenspace of lambda equal to -1. So let's define w exactly as we did before. So it's x minus x dot y all over y, the magnitude of y squared times y. Then in this particular case, this will just be -1, 1, 0, minus x dot y. Now, we already calculated x dot y, right? So -1 times 1, so we have -1. Here we have 1 times 0, and here we have 0 times 1. And so we're just going to get -1 for the x dot y divided by the magnitude of y squared. Now, what is the magnitude of y squared? We square this, we add it to that squared, we add it to that squared. I'm sure you see we just get 2. So we have 2 here. And that now what's left is just what is y, and so y is just 1, 0, and -1. Okay, so here, what does this end up being? Well, the negatives here will cancel, and so we have -1, 1, 0, and then plus a half, 0, and then here we have -1/2. And just to simplify everything further, this is just -1/2, because -1 plus a half is just -1/2. Here we have 1, and here we have -1/2. Okay, so what is the important thing to keep in mind about this? Because w is a linear combination of x and y, you see this explains why it's a linear combination of x and y. It is going to be an eigenvector, sorry, for lambda equal to -1. Okay, but also, and so also, if we multiply this vector by any scalar, it's also going to be an eigenvector. So let's say v is equal to 2 times w. The reason why I do this is just because I don't like fractions too much, and I'm trying to get rid of the fractions in our eigenvector. So we're going to set v here equal, v is 2 times w, so we just get -1 to -1. Okay. So there we have finally found an eigenvector which is orthogonal to y. You can check this yourself if you want. W is orthogonal to y. Great. In other words, this set of vectors if I take, sorry, not w, I said v, I should have said v. Well, both v and w are orthogonal, but v and y are orthogonal. It's an orthogonal set. Okay, good. So in other words, it's orthogonal, it's 2 vectors, and they're both eigenvectors for lambda equal to -1. So we can set b -1 equal to just the normalization of v and y. So let's calculate that quickly. Y, the normalization of this is just going to be, well, remember what y is, it's this vector here. So it has length √2. So we have 1 over √2 here, we have 0, and we have -1 over √2 here. Great. Right, so that's going to be what y is. Now, what is v hat? What is the normalization of v? Well, this is just going to be, you divide this vector by its magnitude. Now, what is the magnitude of v? Well, it's going to be the square root of the square of its components. So -1 squared plus 2 squared plus -1 squared. I'm sure you see this is just √6. So what do we get here? We get -1 over √6. Here we get 2 over √6. And here we get -1 over √6 again. And I've written this extremely badly, but anyways. So this is what the normalization of v is. Great. Now these are going to be our two vectors here. So I'll just copy them. I'll copy this one first. So our first vector is this one, which I'll put here. And our second vector is this one here. Great. And so finally we found our orthonormal basis for the eigenspace corresponding to lambda equal to -1. Okay, so after a long enough time, we finally got there. We've got this orthonormal basis for lambda equal to -1. Okay, and we've actually already seen what the orthonormal basis for lambda equal to 3 is. We can just take that as 1 over √3, 1 over √3, and 1 over √3. It's really difficult to draw vectors when they have fractions and roots. Okay, anyway, so this is we found all the orthonormal bases that we need, this one and this one. And so we're ready to produce the P and the Q in the orthogonal diagonalization. So let's do exactly that. So Q, we're going to define, remember what is Q? It's the columns that we form from these vectors. So we can choose them in any order we like. And so why not just choose like this one first, and then this one, and then this one here. And then you see we'll get this matrix 1 over √2, we have 0, and then we have 1 over square root 2 again. And then here let's take -1 over square root 6, 2 over square root 6, and here -1 over square root 6. and here we just have 1 over root 3 and 1 over root 3 and also 1 over root 3. So we take that to be our Q, and then we can define D as what matrix? D will be, well, let's just check here. This, remember, is C1, C2, and C3. So we have to ask the question, where does C1 belong? Well, it belongs in B negative 1. So the first entry here will be negative 1. Okay, where does C2 belong? Well, also, C2, this column vector here, is given here, which also belongs to B1. So it's also negative 1 here. Now we move to position 3, 3, and we ask, where does C3 belong? Well, it belongs here. Let's give it a different color, why not? So C3 belongs in this set, because that's where it is. And then we write 3 here. Is it... yeah, so we write 3 there. Oh, I seem to have made a bit of a mistake. The eigenvalue we calculated earlier was 2, and so this should be 2. I do apologize, this is not correct. If I just go back up here, well, the mistake I made is that this should be 2. Okay. But anyways, it doesn't change anything other than this number becomes 2. So then we have zeros here, a 0 here, and a 0 here, and a 0 here, and 0 here, and a 0 there. And then it's just left to check that Q times D times Q transpose is just equal to our original matrix, which, if you remember, was 0, 1, 1, 1, 0, 1, and then 1, 1, 0. All right, so that just gives you a lengthy example of how we orthogonally diagonalize a matrix. Or we've given 2 examples here. And this last example really does show you that we have to sometimes take care. So the care that we needed to take was because of this set over here. And these vectors, although they were a basis for the eigenspace E sub lambda 1, they weren't an orthonormal basis. So all of this calculation we did over here in yellow was just to form orthonormal, these orthonormal bases over here. All right, so that does it for this video.